Watch this video till the end and grab 7 to 10 marks in your CBSE 10th board exam. Wondering how? Well, the light chapter is more than just theory. The 7 to 10 marks come in the form of definitions, laws, ray diagrams and numericals. I will cover all these topics with exam hacks and tips at every step along with solving some prior year numericals. Stick with me till the end of this video where I will share an amazing trick and you will never get confused between mirrors and lenses. Let us start by answering the question, what is reflection? When light falls on a polished surface like mirror, it bounces back instead of passing through. This phenomenon is called reflection. Sometimes in exam, this question is also asked in the terms of why can we see ourselves in the mirror, and answering this can give you 2 full marks. Let us move to what are laws of reflection. Well, there are some general laws of reflection that are applicable to all kinds of surfaces. The first law is the angle of incidence is equal to the angle of reflection. Second law is the incident ray, reflected ray and the normal to the mirror all lie in the same plane. Usually this question is asked for 2 marks where you have to write the law and the equation, and if it is asked for 3 marks, write the law, the equation and also draw the diagram. Moving to image formation by a plane mirror. When we see in a plane mirror, it is a reflection of ourselves which is usually virtual and erect. It is the same size as that of the object. The object and image are equidistant from the mirror and the image is laterally inverted. That is, your left and right change itself. Let us now see what are spherical mirrors. There are 2 types of spherical mirrors. One is a concave mirror and other is a convex mirror. A concave mirror has an inward polished surface, whereas a convex mirror has an outward polished surface. We will now learn some important parts of this mirror which are important for our numericals. So the center of the mirror is called the pole of the mirror, and the line that passes through this is called the principal axis of the mirror. Every mirror is part of a circle and the center of the circle of which it is part of is called the center of curvature of that mirror. The distance from the pole to the center of curvature is called the radius of curvature of that mirror. And now a concave mirror converges all the reflected rays and hence it is also called a converging mirror. And the point where the reflected rays converge is called the focus, and the length from the pole to the focus is called the focal length of the mirror, and it lies in front of the mirror for a concave mirror. And a convex mirror diverges all its reflected rays, hence it's called a diverging mirror, and the point where all the reflected rays diverge from is called its focus, and the length from the pole to the focus is called the focal length of the mirror, and it lies behind the mirror in this case. Now, for spherical mirrors that are less curved, there is an important relation between the radius of curvature and the focal length. That is, the radius of curvature is 2 times the focal length. This is very important for our numericals. Let us see some rules for drawing ray diagrams. We will see how each reflected ray acts for different cases of incident rays. Case 1. If the incident ray is parallel to the principal axis, the reflected ray will pass through or appear to pass through the focus. Case 2. If the incident ray is passing through the focus or appearing to pass through the focus, the reflected ray will be parallel to the principal axis. If the incident ray is passing through the center of curvature, the reflected ray traces its path back. And for an incident ray that falls at an angle I at the pole, the reflected ray will be at an angle R which is equal to I at the pole. Let us now see the image formation for a concave mirror. We will be moving the object from infinity and bringing it closer to the mirror and see where the image is formed. We will understand the size and the nature of the image. Understanding this helps with our ray diagrams which come for 5 marks. Remembering this will also help you in your numericals. I will share an amazing trick to remember this at the end of this section. So let us start with case 1. If the position of the object is at infinity, the position of the image will be at focus and the size of the image will be highly diminished and point size. The nature of the image will be real and inverted. Case 2. If the object is moved to beyond C, the position of the image will be between C and F. The size of the image will be diminished. The nature of the image will be real and inverted. Bringing the object to at C, the position of the image will also be at C. The size of the image will be same as that of the object and the nature will be real and inverted. Case 4. Bringing the object between C and F, the image will be beyond C. The size will be enlarged. The nature will be real and inverted. Bringing it further closer to focus, the image will be at infinity, highly enlarged, real and inverted. Bringing it between F and P, the image will be behind the mirror, enlarged and virtual and erect. This table summarizes what we just saw, and the trick to remember this is, as we keep moving the object closer, the image keeps going farther away from the mirror and it also gets bigger. Let us now move to uses of a concave mirror. This is one of the board exam's favorite question and it is asked for 3 marks generally. If asked for 5 marks, you should write where it is used and why it is used. So let us see where and why it is used. It is used in torch lights, searchlights and headlights to get powerful straight beams of light. It is used in dental mirrors and shaving mirrors to get enlarged images. It is also used in solar furnaces to concentrate sunlight to produce heat. Let us now move to the image formation of convex mirror. Here there are only 2 cases. Case 1, if the position of the object is at infinity and the position of the image is at focus. The size of the image will be highly diminished and point size, and the nature of the image is virtual and erect. Case 2, anywhere between infinity and the pole, the position of the image will be between F and P behind the mirror, and the size of the image will be diminished. The nature of the image will be virtual and erect. So this table again summarizes what we have for convex mirror, which is again important for our sums and ray diagrams. So uses of convex mirror, again you need to write where and why to get your full 5 marks. So it is used in rear view mirrors in cars because they give virtual and erect images to the driver, and it has a wider view to the driver as it is curved outwards. Let us now learn the sign convention for mirror. The best trick to remember sign convention is to remember your number line. How do we have our number line? All positive numbers to the right of the 0. All negative numbers to the left of 0. All positive numbers above 0. All negative numbers below 0. Now, you're just placing your mirror at 0. You assume your pole is at 0. Similarly, you consider all distances behind the mirror to be positive, in front of the mirror to be negative, above the principal axis positive, below the principal axis to be negative. So, this is how you can remember sign convention. Now, from this sign convention, we can gather some basic inferences that can help us in our numericals. Object distance will always be negative because you place the object in front of the mirror. Object height will always be positive because you keep it erect. Second, for a concave mirror, the focal length will be negative because it is in the front of the mirror, and for a convex mirror, the focal length will be positive because it is behind the mirror. And if the image height is negative, it is understood that it's a real and inverted image, and if it is positive, it is understood that it is a virtual and erect image. Let us solve a numerical so that we are thorough with what we have studied. This question was asked in the All India 2016 exam for 3 marks. The image of an object formed by a mirror is real and inverted and is of magnification -1. If the image is at a distance of 40 cm from the mirror, where is the object placed? Where would the image be if the object is moved 20 cm towards the mirror? So let us write down what we know from the question. We know that the magnification is -1. We know that the image is real and inverted, which implies that the mirror is concave mirror. Since the image is real and inverted, the image is also in front of the mirror, which implies that the image distance is -40. Now from the magnification, which is -1, we can understand that the object is placed at C because the image is of the same size of that of the mirror. Therefore, the object and image both are at C, which is 40 centimeters. Moving to the second part of the question, if the object is moved 20 centimeters towards the mirror, that is, you go towards 20 centimeters further, your object distance will be at -20 and your radius of curvature is 40. So if radius of curvature is 40, the focal length r by 2 would be -40 by 2, which is -20 centimeter. So your focal length is -20 and you have placed your object also at 20. This means that the object is at focus, so the image will be at infinity. This is how remembering the table can help you solve those numericals which do not need any formulas. Let us move to mirror formula. 1 by V plus 1 by U is equal to 1 by F. This is the mirror formula. Here, U is the object distance, V is the image distance, and F is the focal length of the mirror. The magnification of a mirror is given by image height by object height also equal to minus V by U, where M is the magnification, H dash is the image height, H is the object height. Now let us solve another numerical where we use the mirror formula. This question was asked again in the All India 2016 for 3 marks. The image formed by a spherical mirror is real and inverted, and the magnification is minus 2. If the image is at a distance of 30 cm from the mirror, where is the object placed? Find the focal length of the mirror and list 2 characteristics of the image formed if the object is moved 10 cm towards the mirror. Let us write what we know from the question. It's a real and inverted image, which implies that it's a concave mirror. We know the magnification is minus 2, and since it's a real and inverted image, it will be in front of the mirror, so your image distance will be minus 30. So magnification is given by minus V by U, so I can write U is equal to minus V by M. So U will be equal to minus of minus 30 divided by minus 2, which gives U to be equal to minus 15 centimeters. Now using the mirror formula, 1 by V plus 1 by U is equal to 1 by F, I can substitute this as 1 by minus 30 plus 1 by minus 15, which gives me minus 1 minus 2 divided by 30. If 1 by F is minus 3 by 30, which is minus 1 by 10, F will be equal to minus 10. This completes the first part of the question. The second part says list 2 characteristics of the image if the object is moved 10 centimeters towards the mirror. So if you move the object 10 centimeters, it is minus 15 minus of minus 10, which is minus 5. So if U is minus 5, that means that the object is placed between P and F, because your F is 10 centimeters. So the characteristics of image which is between P and F is the image will be behind the mirror, it will be enlarged, virtual and erect. Since we have understood reflection, let us now move to refraction and try and answer the question, what is refraction? When light travels from one medium to another, it bends, and this bending of light is called refraction. This question is usually again twisted and asked in the terms of why a pencil appears bent when put in a glass of water. It usually comes for 2 marks, and writing this answer for that question can fetch you 2 marks. Let us now understand what are laws of refraction. Well, there are certain laws of refraction which are applicable to a given pair of media and a given color of light. The first law is incident ray, refracted ray and the normal to the interface of 2 media lie on the same plane. The second law of refraction is also called the Snell's law, which states that the ratio of the sine of the angle of incidence and the sine of the angle of refraction is a constant for a light of given color and a given pair of media. Writing those 2 conditions is very important because Snell's law only holds true in that case. What is Snell's law is usually asked in the exam for 2 marks, and writing it along with the condition can fetch you those marks. Writing the laws along with the formula can give you 3 marks, and writing the laws, formula and the diagram can give you 5 full marks. Let us see how a glass slab helps you in refraction. The basic inference that we draw from here is when a light is incident on a glass slab, it refracts and then again emerges out through the glass slab. And the light generally bends towards the normal when it moves from rarer medium to a denser medium, and the light bends away from the normal when it is traveling from a denser to a rarer medium. And the incident ray and the emergent ray will be always equal or will be in the same line. Usually this question is asked to explain the inference for 2 marks, diagram and the inference, and get your full 3 marks. Let us now understand what is refractive index. Well, the amount of change in the direction of light when it is traveling from one medium to another measured in terms of refractive index. It is a dimensionless quantity which is generally the ratio of the speed of light in medium 1 compared to the speed of light in medium 2. That is, refractive index of medium 2 with respect to medium 1 is given by speed of light in medium 1 divided by the speed of light in medium 2. If measured against speed of light in vacuum, which is 3 into 10 to the power 8 meters per second, it is called absolute refractive index, where it will be given by speed of light in vacuum divided by the speed of light in the medium. Writing the definition of refractive index along with the formula can give you 3 marks, along with the diagram can give you 5 marks. Right. Let us now solve a numerical on refractive index to understand it better. This question was asked in the year 2020 for 3 marks. The refractive index of a medium X with respect to medium Y is 2 by 3, and the refractive index of Y with respect respect to z is 4 by 3. Find the refractive index of z with respect to x. If the speed of light in medium x is 3 into 10 to the power 8 meters per second, calculate the speed of light in medium y. So let us start by writing what we know first. We know the refractive index of x with respect to y is equal to 2 by 3 and the refractive index of y with respect to z is 4 by 3. We know the speed of light in medium x is 3 into 10 to the power 8 and we need to find the refractive index of z with respect to x and the speed of light in medium y. So refractive index of x with respect to y means that it is vy by vx, where vy is the speed of light in medium y and vx is the speed of light in medium x. Similarly, the refractive index y with respect to z implies it is speed of light in medium z to the speed of light in medium y. So from this we can multiply both of this to get the refractive index of x with respect to z, where we can write vy by vx into vz by vy. This will give us vz by vx, which is nothing but the refractive index of x with respect to z. So this is nothing but the multiplication of refractive indices xy and yz, and in turn taking the inverse of refractive index of z with respect to x will give us the refractive index of x with respect to z. So substituting the values, 2 by 3 into 4 by 3 will be equal to 8 by 9 and the reciprocal of this will be 9 by 8, which is the refractive index of x to z. Now the refractive index of x to y is vy by vx and so vy will be equal to refractive index of x with y into vx, that is 2 by 3 into 3 into 10 to the power of 8, which is equal to 2 into 10 to the power of 8 meters per second, which is the speed of light in medium y. Let us now understand refraction through spherical lenses. When you take two convex mirrors and merge them together, you can make a convex lens, and taking two concave mirrors and merging them together end to end can give you a concave lens. Now let us understand some important parts of these lenses to help us with our ray diagrams and numericals. The center of the lens is called the optic center of the lens and the line that passes through it is called the principal axis. Now again, a lens is part of two circles because it is formed by two mirrors, and the two centers of those circles are called the centers of curvature or the two focal points, which are 2f1 and 2f2 or c1 and c2. Similarly, for concave lens, it is also part of two circles, giving it two center of curvatures or two focal length points. For a convex lens, which is also called a converging lens, it converges all the refracted rays to a point on the principal axis, which is called the focus. Now there are two focal points for a lens depending on which side the incident ray is coming from. Now the length from the optic center to the focus is called the focal length of the lens. Similarly, a concave lens diverges all the refracted rays from a point called its focal point, and there are two focus points for a lens depending on which side the incident ray is coming from. Again, the length from the optic center to the focal point is called the focal length of the lens. Let us now see some ray rules for lenses again. So case 1, if the incident ray is parallel to the principal axis, refracted ray will pass through or appear to pass through the focus. If the incident ray is passing through or appearing to pass through the focus, the refracted ray will be parallel to the principal axis. And if the incident ray is passing through the optical center, the refracted ray will be passing through without any deviation. Let us now see the image formation for a convex lens. Again, this is going to come for 5 marks in terms of ray diagram or numericals. So let us see it case by case. Case 1. If the position of the object is at infinity, the position of the image will be at 2f2. The size of the image will be highly diminished point size. The nature of the image will be real and inverted. Case 2. If the position of the object is beyond 2f1 and the position of the image will be between 2f2 and f2, size of the image will be diminished and the nature of the image will be real and inverted. If the position of the object is at 2f2, the position of the image will be at 2f2, the size of the image will be same and the nature of the image will be real and inverted. If the position of the object is 2f2 and f1, the position of the image will be beyond 2f2, the size of the image will be enlarged, the nature of the image will be real and inverted. Case 5, if the position of the object is at f1, the position of the image will be at infinity, size will be highly enlarged, the nature will be real and inverted. Case 6, if it is f1 and o, the position of the image will be same side of the object, enlarged, virtual and erect. Again, a similar table for convex lens, and if you notice it is very similar to that of a concave mirror, where moving to a concave lens where we have only two cases. If the position of the object is at infinity, the position of the image will be at f1 and the size of the image will be highly diminished and point sized. The nature of the image will be virtual and erect. Case 2, if the position of the object is between infinity and o, position of the image will be between f1 and o and the size of the image will be diminished, virtual and erect. This table again summarizes it for the concave lens. The sign convention for lenses is exactly similar to that of the mirrors, where we again follow the number line rule, where the optic center of the lens is considered at 0 and the principal axis is x-axis. All the distances measured to the left of O are considered negative and right of O are positive. Above the principal axis is positive and below is negative. So the inference we draw here is the object distance, and the object distance will always be negative. The object height will again always be positive, and for a concave lens the focal length will be negative, and for positive for a convex lens. And if the image height is negative, it is real and inverted image, and if it is positive, it's a virtual and erect image. So let us now see the lens formula, which is 1 by v minus 1 by u, which is equal to 1 by f, where u is the object distance, v is the image distance, and f is the focal length of the mirror. And magnification is h dash by h or v by u, where m is the magnification and h dash is the image height and h is the object height of the mirror. Let us see power of a lens, which is given by 1 by f, where p is the power of the lens and f is the focal length of the lens. Let us solve a numerical on this to understand these better. This question was asked in central paper for 2009 year for 3 marks, where how far should an object be placed from a convex lens of focal length 20 centimeters to obtain a real image at distance of 30 centimeters from the lens. Determine the height of the image if the object is 4 centimeters tall. So what do we know here? We know that the focal length of the lens is 20 centimeters and it's a convex lens, so it's a positive focal length. It's a real image, so the image will be behind the lens, so it will be v equals to positive 30 centimeters. The image height is 4 centimeters and we need to find the height of the object. The magnification, if we know the magnification, we can divide it by the image height to get the magnification, which is given by v by u, and since we are not aware of the u, we need to find using the lens formula, which is 1 by v minus 1 by u equal to 1 by f. So 1 by u will be equal to 1 by v minus 1 by f, which is 1 by 30 minus 1 by 20, which is 2 minus 3 by 60, which is minus 1 by 60. 1 by u is minus 1 by 60, so u will be minus 60 centimeters. So the magnification now will be v by u, which is 30 by minus 60, which is minus 0.5. And the object height will be equal to h dash by m, which is 4 divided by minus 0.5, which will be equal to minus 8 centimeters. When they add a ray diagram to this question, it comes for 5 marks. Now here's an amazing trick that you've been waiting for from the start of the video, such that you cannot get confused between lenses and mirrors. M for mirror and M for magnification, so there will be a subtraction in the magnification formula for mirrors. So it is minus 1 by u. So since you have put the subtraction in the magnification, you don't have to put it in the mirror formula. So it becomes 1 by v plus 1 by u is equal to 1 by f. And you can remember the lenses in the opposite way by saying lens S for subtraction. So the lens formula has a subtraction. It is 1 by v minus 1 by u. And since you have already put a subtraction here, you don't have to put it in the magnification, which will be v by u. This is how you remember or do not get confused between mirrors and lenses. Use these tricks so that you do not go wrong in your exams. So that completes your reflection and refraction chapter, where we covered all definition, laws, ray diagrams and numericals with exam trips and prior year numericals, which will guarantee your 7 to 10 marks. Want to add 10 more marks to your board's bucket? Watch my videos on life processes here. Subscribe to the channel for more videos. Before you go, leave a comment below if you want a step-by-step video on how to draw ray diagrams, which will make these 7 to 10 marks a sure shot in your exam. Like this video and share it with your other 10th class friends so that everyone can convert their concepts to grades.